Okay, good morning, everyone. So last time we were starting to talk about what will eventually be the shell model of multi-electron atoms. And we were talking about orbitals, which I will remind you, orbitals are single electron. So we're not trying to describe all the electrons together yet. Single electron eigenstates of a central potential Hamiltonian. And so it's a little bit vague or fuzzy because we're not telling you exactly what central potential Hamiltonian you should choose. Basically, you are supposed to choose it based on having perturbation theory converge more quickly. And so for each electron, we write down a single electron Hamiltonian, okay, which is the kinetic energy term. And then if you want to be fancy, you can actually lump in some of the relativistic effects into that, because there's a p to the fourth term divided by the speed of light squared that comes from relativity, and you could actually put that in there if you want. And then you also put in some potential, but this is a potential that you sort of get to invent. This is chosen to approximately mimic the effects of the nucleus and all the other electrons. Okay, and we do this for each electron. Okay, so K1 up to Z sub E. And then there are different schemes that are similar to this called the Thomas Fermi approximation and other things. But they all basically boil down to you choose an unperturbed Hamiltonian like this that's simple. And so your total unperturbed Hamiltonian, I'll write total here, is just the sum of over all the electrons from K equals 1 up to, I'm going to call it Z sub E today, for the individual Hamiltonians. So I'm distinguishing Z sub E from Z because for an atomic ion, it may be that the number of electrons that you have is not equal to the number of protons if it's a non-neutral ion. Okay, so in principle, they could be different. And then there's the rest of the Hamiltonian, whatever it is. Okay, which is going to be sum over all the electrons. And now I subtract the part that I added in because that was just something I invented. And then I put in all the things that actually come from physics. There's the proton attraction. There's the electron-electron repulsion, which doesn't carry a Z on it. And then there's the spin-orbit coupling, which involves the dot product of the orbital with the spin. And then there are other things. Okay, and so the idea is if you've chosen your U correctly, then when you treat that W as a perturbation, it will hopefully sort of converge. Okay, now when you do that, the unperturbed energies are just the sums of the individual unperturbed energies. So this is the sum of the H0K eigenvalues. And so the orbitals are labeled by the quantum numbers of those eigenstates. So orbitals labeled N and L, except then, well, N is a quantum number that starts at 1. It's very important to know where these things start from. There was some confusion on the midterm with, and on previous homework assignments with, for the harmonic oscillator, the principal quantum number starts at 0. But for the hydrogen atom, it starts at 1. It just depends on the system and how you're labeling things. But n starts with 1, and the orbital angular momentum starts at 0, and it goes up to n minus 1. But then you replace that by your letter code, which is S. For 1, it would be P, etc. Okay, and so this labeling is just like hydrogen. But where it differs from hydrogen is in the actual energy eigenvalues, because our U is not the same thing as V for hydrogen. So I'll write but here. If you label as a function of energy, and this is going to be sort of qualitative, but we know the ground state down here is going to be a 1s. And then above that, there will be a 2s. But then the 2p, unlike for hydrogen, is not degenerate anymore. It's higher. Okay, so not degenerate. Okay, the 2p is higher than the 2s. Okay, and if you go to 3s here, the same thing happens. Oh, by the way, horizontally, what I'm doing here is increasing angular momentum is going to the right. But angular momentum is quantized into integers. Okay, so there's a 3s, a 3p is higher than the 3s, unlike for hydrogen. The 3d is up here, again, unlike hydrogen. And then it turns out the 4s is slightly below the 3d. Okay, so they're approximately degenerate by accident. But the 4s is slightly lower. And when I say slightly lower, what I really mean is it's slightly lower for a choice of U, the potential U, that makes everything work. And that's a little bit of a fuzzy statement because for different atoms, the choice of U will be slightly different. But nevertheless, that's the idea. Okay. So those are the, that's sort of a rough sketch of the first few orbital energies. And by the way, this is qualitatively similar to a system that we've already studied in Physics 660 last semester, namely a particle in a square well. So if you look back at figure 8.3.2 in the notes, sometime when you have a chance, that was a particle confined to a sphere. You will notice that the same sort of thing happens where for a given angular momentum, the lowest state for that angular momentum gets higher in energy as you go to higher angular momentum. Okay, and there are no accidental degeneracies in that system at all. And it's similar to here. There are no actual, when I put in the full U rather than the, say, approximation of just treating the nucleus, then this state has no reason to be degenerate with that anymore. That's a very special property of the hydrogen atom. And these states are not degenerate. They're just going up in energy. And so it's sort of an accident that these two happen to be close in energy. Okay, so now having cataloged those states, we can put in our atom, we can put pairs of electrons into the same orbital, whichever one is the lowest available one in energy. But if we put them in the same orbital, that's only if they have the opposite spin, because they can't have the same quantum numbers for all their different observables. So if and only if the spins form an antisymmetric state, And for pairs of electrons, forming an antisymmetric state means forming a spin 0 state. Because we constructed the states that you get by putting together two spin 1/2s, and the antisymmetric one was spin 0. Okay, that was one spin up, the other spin down, minus the spins in the opposite configuration. And so the idea is, just considering pairs of electrons, you have a state which you can write as an orbital part, tensor product with a spin part, and the spin part is necessarily spin 0 because that's antisymmetric, and the orbital part is therefore necessarily symmetric. Okay, and so the whole state is antisymmetric, which is what our postulate about the symmetry properties of identical fermions told us it had to be. Okay, so now if we just make a list of what we can do for higher electron atoms, the first state we're going to fill is the lowest one here, the 1s. And so if we have a 1s and we fill it as much as we can, that means we can fit 2 electrons in it. And so that will accommodate hydrogen and helium atoms, which we've already studied. The next lowest one is the 2s. So once we've filled up the 1s, we can fit 2 more electrons in there. And the elements that do that are lithium and beryllium. Okay, but once we've filled that up, then we have to go to the next highest state, because we filled up everything we can do with those orbitals. And so there it's 2p. Okay, and that can fit how many electrons? 6. So why is it 6? It's 6 because it's 2 for spin times 2l plus 1. So that's 3. Okay, so this is for spin, and this is the 2l plus 1 factor. Okay, so that can fit 6 electrons. And so if you're just piling electrons into orbitals, that can accommodate the elements boron, carbon, nitrogen, oxygen, okay, etc. And then for 3s, that's an S wave state again. So now it's got only 2. So that fits 2 electrons. Those are sodium. And is that manganese or magnesium? I can never remember which one. I get those confused. Anyway, 3p.
Magnesium.
Magnesium, thank you. 3p can fit 6 again, same counting. It's spin times 2l plus 1. And so off we go with all the other elements. Okay, and then when we get to 3D, that's where this coincidence comes into play, where the 4s and the 3D happen to be roughly degenerate. The 4s is empirically slightly lower for no particularly good reason, it just is. So for the moment, I'll put it like this. So there's 3D and 4s. The 3D can fit 10, and the 4s can fit 2. And so when I'm filling those up together, that will fit the next 12 elements, etc. So generalizing the little diagram that I had that showed the energies, here's the shell filling order. And so if we were to do some complicated variational principle analysis of atoms, we could presumably verify this, but it's sort of a lot of work. Okay, these are the lowest energies, 3p. And then we get to 4s and 3d. 4s usually fills first, then 4p. And then it turns out the 5s is slightly lower than the 4d. Then it goes 5p, and then the 6s, 4f, and 5d are approximately the same energy. Then 6p, and then 7s, 5f, and 6d. Okay. So this gives rise to the concept of electron configurations. If you've decided what your atom or your ion is, then you can write down or summarize how these orbitals are filled in the following way. So for hydrogen, you just write, there's only one electron, so you just write 1s with a superscript 1 to just tell you that you've put one electron in that orbital, which you're free to do because any orbital can fit up to 2 electrons. So for helium, there's an electron configuration which is 1s2, meaning you've put both your electrons in there. But it's important to realize that's just for the ground state. We studied the ground state 2 different ways, with variational principle and then first with perturbation theory. But then we went on to study the excited states, which were like 1s, 1p. So a lot of times when we specify the electron configuration, we're really specifying for the ground state. And there are many other possible electron configurations for a given atom that are excited states. So in any case, for lithium, we would say 1s2, and then 1 electron in the 2s state. And you can continue going on like this. For carbon, it would be 1s2, 2s2, and then 2p2. For nitrogen, for example, it's 1s2, 2s2, 2p3. And then if you want one that's really complicated, there's, I'll just show off by doing mercury. It's 1s2, 2s2, 2p6. You don't have to write this down if you're taking notes because you can always look these things up. But just to give you an idea, it looks like this. You just fill up all these orbitals or shells. 4s2, 3d10, 4p6. Notice the exponent is determined by the letter code. The maximum exponent is determined by the letter code. For a D, it's going to be 10 because a D has orbital angular momentum 2. 2L plus 1 for L equals 2 is 5, but then there's a factor of 2 for spin. Okay, so 4p6. Where was I? 5s2. 4d10. 5p6. 6s2. 4f14. 14 because it's 7, which is orbital angular momentum 3 times 2 makes 6 plus 1 times 2 for spin. And then 5d10. And if you add up all those electrons in the exponent, that's 80. So that's the atomic number. Actually, technically, the atomic number should be the number of protons. So we're talking really here, assuming that it's a neutral atom. Okay, and as a general principle, I've already drawn this on the little energy sketch. For a given n, smaller L states tend to have lower energy. And this is, again, qualitatively similar to what we found when we studied the particle trapped in a spherical well. And there's a qualitative reason for that, or one of the qualitative reasons is that electrons with smaller L tend to be closer to the nucleus. And the closer they are to the nucleus, the more that the nuclear charge attracting them is more important, which lowers their energy. Another way of thinking about it is that they're inside the screening cloud from the other electrons. So that'll tell you qualitatively why, for example, if we go back up here, why the 4s is lower than the 3d and why the 6s is lower than the 4f. But it doesn't actually tell you in detail why these are approximately the same or why the filling order is in that order. That's just something you have to get by a more complicated than we are willing to do analysis of the unperturbed energy levels. Okay, so for any atom, you can write down the electron configuration, but that's not all we want to know about atoms, because that's really more or less telling us about the energy of the state. We would also like to know about the angular momentum of the state. So we also want to describe the angular momentum. And unfortunately, to do that requires an approximation. And so to set up the approximation, let's at least do some things that we can really define rigorously. We can define the total orbital angular momentum as just the operator that you get by summing up all the individual orbital angular momenta. So that's an observable because notice it has to be symmetric under interchange of any two orbital angular momenta. If I just did a sum over sum of them or just took one of them individually, that would be a Hermitian operator, but it would not be an observable. So we can do the total orbital. We can similarly do the total spin for each of our electrons. Okay, and those are observables. And then there's J, which we get by just adding those two things together. That's the total angular momentum. By the way, we're leaving out the angular momenta of the nucleus, which will often, for the same element, be several different things, because you can have different nuclei depending on the number of neutrons in the nucleus. And so the spin is, well, it's probably not going to be spin 1/2, but it might be very different things for different isotopes of the same element. Okay, now the thing about these operators that's nice is that they commute with most of the Hamiltonian, including the part we were treating as a perturbation, other than the spin orbit part. Okay, and the reason is if I take this total angular momentum, total orbital angular momentum, and commute it with this, right? It's the combination is going to give me something that's this orbital angular momentum with that one correlated. Okay, and so that term, that one term, is what's going to cause difficulty and say that we can't say exactly that our states are eigenstates of these operators. But nevertheless, what we can do is we can say, let's treat that term as a perturbation. Okay, and if it's small enough, then as an approximation, the following will work. This is called the LS, or the Russel-Saunders, I guess, coupling approximation. Okay, and this is, as a note, this is not as good of an approximation for very large Z. And that's partly because the L dot S term gets larger, relatively speaking, for very large Z. Okay, but the statement of the approximation is that the full Hamiltonian eigenstates are almost eigenstates of the following set of commuting observables, namely L squared, S squared, J squared, and J sub Z. Okay, so it's not exactly true, but it's close to being true. And within that approximation, the J sub Z is a degeneracy because the energy won't actually depend on that. It will depend on L, S, and J, though. Okay, and so in particular, these are not going to be eigenstates of the product basis. Now, if I do something like add an external magnetic field, then things get much more complicated because an external magnetic field is going to want things to be eigenstates of, if it's in the Z direction, it's going to want things to be eigenstates of L sub Z and S sub Z, and things will get very mixed up. Okay, but we're not assuming that there's any external field. And so this Russel-Saunders coupling approximation is just asserting that our states are eigenstates of these operators. And to denote them, we write spectroscopic notation, which we've already seen. And so really all we're doing here is generalizing what we've done before for spectroscopic notation. We write 2s plus 1. Now, when we dealt with hydrogen, s was 1/2, always. And when we dealt with helium, s was always 0 or 1, but now it can be something else. And we write L, that's the total orbital angular momentum, and then we write J as a subscript. And this is sometimes called a term, or a Russel-Saunders term, or an LS term. Okay, and then as usual, the orbital part we replace by a capital letter, but according to the same code. So now it's going to be capital S, capital P, capital D, capital F, etc. Okay, and so the difference between this letter is this letter is for the total spin, whereas the lowercase letters we were writing down before were for the individual spins of the individual electron orbitals. Okay, so for a given term, which is really a code for a set of states, there's a degeneracy that comes about from here. And so the degeneracy of each one of these will be 2j plus 1. So this is important because later on we're going to want to be counting carefully how many states there are, because for one thing, when we take an atom and figure out how it divides up into different terms, we'll want to make sure that the total number of states that we get is the total number of states that's possible to construct out of that many electrons. So the degeneracy is 2j plus 1, and I'll put in parentheses, this is all not counting the nuclear spin. And the nuclear spin could be anything. So for example, for the most common form of helium, the nuclear spin is 0. And so there's no degeneracy at all from that. But of course, for the hydrogen atom, the nuclear spin is 1/2, so there's an additional degeneracy of 2. Okay, so now, given an electron configuration, we can construct all the possible terms, all the possible angular momentum configurations. You'll get some practice doing this for homework. So we'll do as many examples as we can in class to prepare you for that. So an electron configuration, again, would be something like this. You can construct all possible terms. But having constructed all possible terms, you're usually particularly interested in which one of them is the ground state. And then sometimes which one will be the next few excited states beyond that. So that's the question that we would like to address next. Which one of these terms is the ground state? So it turns out just for more complicated atoms, just constructing the possible terms is the hard part. And then figuring out which one is the ground state is not so bad, because there's a set of rules called Hund's rules that tell you how those go. So Hund's rules are really empirical, meaning they're just summarizing the results of lots of observations. Although we'll be able, I think we'll probably get to this in the next lecture, we'll be able to give a sort of a hand-waving justification for them. But there's actually been a lot of debate about to what extent the hand-waving argument in favor of Hund's rules are actually reflecting what's really going on. Anyway, for these are just the rules, and you can just apply them. And I actually don't know of any exceptions to Hund's rules, even though every textbook says, oh, these are just approximate things. But I spent quite a while trying to find an exception, and I couldn't find one. So if you can find one, let me know. So the Hund's rules are for a fixed electron configuration. So you can't compare different electron configurations with these rules. Okay, so you might have, you've constructed a bunch of possible terms, and the statement, the Hund's rule number 1 says the LS multiplet term with the largest S will have the lowest energy. So you just scan the terms that you construct and you figure out which one has the largest S, and that's the winner, that's the ground state. Except that doesn't always tell you what you need to know, because maybe there are several terms that all have the same S. So if that's true, then to break the tie, the second rule comes in and says, so maybe I'll write it this way: if several L's have the same S, then the largest L has the lowest energy. By the way, when I say I don't know any exception to Hund's rule, I'm really talking only about predicting the ground state, although you can also apply Hund's rules to higher excited states. Okay, but technically Hund's rules are supposed to apply to the ground state only. And the other thing is it actually works even in cases where the Russel-Saunders approximation itself is known not to be terribly good, which is for things like, for example, a lead atom or something with very high Z. Then we know the Russel-Saunders approximation is starting to break down. And yet, nevertheless, if you use the Russel-Saunders approximation and use Hund's rules within it, it correctly tells you what's the angular momentum of the ground state. So it works better than you might have any right to expect.
Professor?
Yes.
I'm just curious, doesn't spin and orbital angular momentum, aren't these were like Hamiltonian or energy or whatever, like they were relevant to the momentum, or they commuted with the momentum, or Hamiltonian, something like that. So doesn't that mean like when they're larger, then we would have more energy?
So it's a complicated thing, because you're having to take into account your different eigenstates of your potential U. And then not only that, but now we're going to be, I'll go way back up here to our Hamiltonian. Now we're going to have to be taking into account this term in the Hamiltonian eventually, which is going to, it just makes things very complicated. Okay, so Hund's rules are just summarizing basically the results of experimental facts about different atoms. And so it's just a set of rules that seem to work, or that basically work in all known examples. I'm not sure if that answered your question, but okay.
Thank you.
Okay, so now what can happen though is you can still have a tie. And so let's say you have several terms that have the same L and S, but different J's. Okay, so within each LS multiplet, that just means a multiplet with the same, or multiplets with the same values of L and S. By the way, I'm using a notation where the capital letter L and S is a number that stands for the quantum number of the corresponding angular momentum, which is also written as a capital letter. So at some point we just run out of letters. And I don't like the notation of putting hats that some books use to denote operators, because then you get too many hats. And so we're sort of using the same symbol for slightly different things. So when I write L and S here, I'm writing really the quantum number, so that the operator, I'm going to put a little aside here. The operator L squared, for example, has eigenvalues h bar squared capital L times L plus 1. And similarly for spin. Okay, that was getting off track a little bit. Within each LS multiplet, the spin orbit coupling is now going to come in and divide those by perturbation theory, divide those into different levels. So the spin orbit coupling splits the state into different levels with different J's. And we know from adding two orbital or any two angular momenta that the possible values of J are the difference in absolute value. Remember, J has to be a non-negative number up to L plus S. So those are all the possible J's you can have. And now we need to know which one of those is going to be the ground state. And the answer turns out to be if an incomplete shell, I'll try spelling that again. If an incomplete shell, so usually there's just one incomplete shell, not always, but usually, is less than or equal to half filled, and the equal is very important, less than or equal to half filled, then the ground state is going to be the one with J equals L minus S. Okay, but if it's greater than half filled, then it's the other one, the more other extreme case, J equals L plus S. And so notice that it's never anything in the middle. It's always the maximum thing you can have or the minimum thing you can have. And it's the minimum thing you can have if I've got too many shells here. If the incomplete shell is less than or equal to half filled. Okay, and so we can sort of draw a picture as to what's going on here. Let's just say, let me graph here energy. Okay, and let's just say that I was going to ignore all this orbital angular and spin orbit angular momentum stuff and just look at the electron configuration. And so then I might have states like this, where I'm only taking into account electron configuration. And there, my energy levels will be divided up into levels that are a few electron volts in spacing, just like for the hydrogen atom. That's what happened for the hydrogen atom. And then I add in my dependence on L and S. So if I look at different L and S, then these things get split apart into different levels with different L's and S's, like so maybe. And then I put in my spin orbit, and that gives energy levels that depend on J's. Okay, and so this might split apart like this. This is the fine structure for multi-electron atoms. This one might split apart similarly. Okay, and so your different L and S are split by usually something on the order of 1/10 of an electron volt or multi-tenths of an electron volts. And these are going to be split apart by 10 to the minus 2 or 10 to the minus 3 electron volts, depending on what atom you're talking about. So this is the fine structure for these multi-electron atoms. And then that's what you're labeling these states by your 2s plus 1 L sub j term notation. Okay, and so what the Hund's rules are telling you is you start off with some electron configuration, let's say that one, and it's telling you the first two rules are telling you which one will be the lowest one. And then the last or the third Hund's rule is telling you of those, which J will have the lowest state there. Okay, so we're going to do some examples just to see if we can see how this goes. And we'll just start with the easiest ones, which we've already done. So for helium, for example, the electron configuration for the ground state is we're going to put them both in the 1s. So it's 1s2. And then there's only one term state. Namely, it had to be spin 0. So I write a 1 there. That's 2s plus 1. Its orbital angular momentum is 0 because I'm only adding together s wave states. Those are both angular momentum 0. So this is an s right here. And then if I have spin 0 and orbital angular momentum 0, the only thing j can be is 0, so I write a 0 here. Okay, and so we don't need Hund's rules to tell us which one wins because there's only one possible term. Okay, but on the other hand, we could also have an excited state for helium, which is, for example, 1s2s. Okay, and so for that configuration, Hund's rules, well, first of all, there are the following states. There's 3s1 and 1s0. So what happened there is the spin could be s equals 0 or s equals 1. But the orbital, I'm still adding together two s wave states. And so the only thing the orbital can be is L equals 0. And so from that, I just look at what are the different ways of combining L and S. First of all, I can add 0 and 0, and I can get 0. Or I can add 1 and 0, and I can get 1. So that's how I know those are the possible terms. And what do Hund's rules tell us? Hund's rules say, Hund's rule number 1 says the s equals 1 is the largest spin, and therefore that should be the winner as for the ground state. Okay, so Hund's number 1 says 3s1 is lower than 1s0. Okay, and we actually worked that out, remember, with our I and J exchange integrals, and we indeed claimed that the spin 1 was lower than the spin 0. We had some argument for that from looking at those integrals, but Hund's rules tell us the same thing. Okay, and then because of that, you don't need rules 2 and 3 because we've already figured out what's the ground state. Okay, those rules are only there to break ties. Okay, so now let's go and graduate to the next state that we can talk about. So let's do boron. Okay, so boron has Z equals 5. And so let's write down the electron configuration. That's always how we start. So we start with the 1s, we fill that up with its 2 electrons. Then we go to the 2s, we fill that up with its 2 electrons. We've done 4 out of 5. So there's 1 remaining, and that goes in the 2p. Okay, so note the 2s fills before the 2p. Okay, and now the 1s is a filled shell. And so when we fill that shell, basically each electron is paired with another electron that has the opposite angular momenta. And so this is, as a filled shell, it's going to have S equals 0 and L equals 0, which is a way of saying that whenever you have a filled shell, you can just completely ignore it as far as its contribution to L, S, and J. It does, a filled shell does nothing. Okay, and then this is another filled one. Okay, so that's the same thing. And so in the unfilled shell, what do we have? So this is different from the other one, the hydrogen and helium, because now it's a 2p, which means the orbital angular momentum is 1. There's only one of those electrons in the 2p, and so it's S equals 1/2. Okay, and so that's the only possible things that you can have for L and S. And so there's only one choice, and therefore we don't need Hund's rules 1 or 2. The electron configuration has told us what L and S are. But we still need Hund's rules 3. So the electron configurations from this are 2s plus 1 Lj is 2p1/2 or 2p3/2. Okay, and so the 2p shell that's partly filled has 6 electron slots, 6 states you can put an electron in, but we've only filled one of them. That's the 2p to the 1. And so J is going to be L minus S, is what Hund's rule 3 tells us. Okay, and L minus S is 1/2. So the ground state will be the 2p1/2 rather than the 2p3/2. There were only 2 choices in this case. So 2p1/2 is the ground state for boron. Okay, and so one way you might write this is you might write boron, you might write the electron configuration, which is really telling you about the energy and something about how it chemically interacts. And you could say, why do we care about the spectroscopic term? And the name gives it away. It's because when you look at transitions between different atoms, the transitions between different atoms will depend largely on the angular momentum. And one of the important reasons for that is there are selection rules, which we will go over a little bit later in the course, that tell you for given transitions, they are allowed or not allowed, or they're highly suppressed, depending on how does the angular momentum change between the two states that you're moving between when you absorb or emit a photon, right? So chemists are more perhaps interested in this stuff. And as physicists, we're more interested in interactions with, especially interactions with photons, with light. And so that's why we care about the orbital and spin and total angular momentum more. Okay, so if you look at a good periodic table of the elements, a lot of times they'll give you this in the fine print, or they might give you this, or if they're really good periodic tables of the element, they'll give you both of these along with the atomic number and the other information about the element. Okay, so we're out of time today. Next time we will go over a bunch more examples of this to try to see some of the tricks, because for larger Z, you do need some tricks, not just to figure out which one's the ground state, but to even enumerate what are all the possible spectroscopic terms that you can have. Especially when you get shells that are more than half filled, things get a little bit tricky. Okay, so we'll do that next time. Any questions on today's lecture? All right, if not, then I will see you all on Monday.
Thank you so much.
Thank you. Have a good week.
Have a good one.
A question from the midterm.
Okay.
Yeah, it's actually the same